Section 3. So far we've looked at light and cameras. Now we turn our attention to the other major component of a camera, the lens. Lenses come in all shapes and sizes, but they have a couple of things in common. They are generally described by their focal length and their minimum aperture. To understand aperture, we first have to understand focal length. Focal length is described as the distance between the nodal point and the sensor when the lens is focused at infinity. That sounds complicated, so let's start by looking inside a lens. Light enters a lens and travels through a series of optics known as elements. The job of these elements is to either collect light, channel light, or focus light. Elements are often arranged in groups and have various concave or convex shapes. As an aside, the elements are described as either spherical or aspherical. Towards the back of the lens, light converges and then inverts and hits the sensor upside down. The point of convergence is known as the nodal point. Going back to our definition, we can now determine the focal length of a lens for a given sensor position. As you can see from the diagram, if we put the same lens on a camera with a smaller sensor, the focal length would decrease because the sensor would need to be closer to the nodal point. Equally, if we put the same lens on a camera with a larger sensor, the focal length would increase. So focal length is relative to sensor size. I know that several of you have a 24-70 full frame lens on your APS-C cameras. Let's see what that means. A full frame sensor is 1.6 times the size of an APS-C sensor. If we divide 24mm by 1.6, we get 15mm. If we divide 70mm by 1.6, we get 44mm. So the 24-70mm lens on APS-C is the equivalent to 15-44mm. We can do the conversion the other way too. A 100mm lens on an APS-C camera has a full frame equivalent of 100mm times 1.6, which equals 160mm. I hope the maths wasn't too much for you. The majority of lenses are designed for full frame cameras. These have been grouped into descriptive names. A standard lens is anything between 35 to 80mm. A wide-angle lens is anything below this, with an ultra-wide being anything below 24mm. A telephoto lens is anything greater than 80mm, with anything over 400mm considered to be a super telephoto. Pictured below are the longest and shortest lenses I could find, a range of 8mm to 1200mm. Focal length affects many things. The foremost is field of view, as you can see from the images on the right. The top picture was taken with an ultra wide angle lens and the bottom photo was taken with a telephoto lens. The next big effect of focal length is on depth of field. Wide angle lenses have a much deeper depth of field to long lenses. There will be more to come on depth of field when we look into aperture later in the course. Another effect of focal length is that distant objects look further away on a wide lens, and the opposite is true for longer focal lengths. With the exception of macro lenses, the shorter the focal length of the lens, the closer the minimum focus distance is. In the case of the 1200mm lens shown on the previous slide, the minimum focus distance was 4.3 meters, whereas the 8mm fisheye has a minimum focus distance of just 0.3 meters. Finally, there's a difference between zoom and prime lenses. There are many arguments for and against owning either, not least the physical size. Zoom lenses tend to be much larger than prime lenses. They also tend to have more elements, which means more glass. The minimum aperture of a lens tends to influence the diameter of its front element. A lens with a big aperture needs to collect more light, and they also tend to have more elements. Some lenses are made of plastic, which is much lighter than metal. The size of a sensor can influence the entire lens size. Small sensor cameras tend to have smaller lenses. Autofocus lenses house stepper or servo motors, which adds weight to the product. Image stabilization lenses add further complication and weight. As a rule, zoom lenses tend to have a poorer resolution than prime lenses. This is particularly true for long zoom lenses. However, there's a huge benefit in having one zoom lens over a bag full of primes. In an ideal world, lenses should have no distortion. Longer lenses tend to suffer from pincushion distortion, where the middle of the lens is squeezed in. And wide-angle lenses tend to suffer from barrel distortion, where the middle of the lens bows outwards. A lens that has no distortion is called a rectilinear lens, where all the lines are parallel. Lenses tend to lose sharpness as you move away from the center to the edges. The hallmark of a good lens is one that remains sharp at its maximum aperture. This shot is looking at the corner of a lens that is focused properly in the center. As you can see, it's a bit woolly. The retail price of high-end lenses is eye-watering. Here we have two 50mm Canon prime lenses. The one on the right is 20 times the price of the one on the left. You'd be pretty hard pushed trying to prove that it's 20 times better. Vignetting is a reduction of an image's brightness or saturation towards the periphery compared to the image center. This is apparent on some lenses, particularly when they are wide open. It is also an effect that can be applied in software to darken or lighten the edges of an image, to highlight the subject as shown in the top picture. Chromatic aberration, also known as colour fringing, is a colour distortion that creates an outline of unwanted colour along the edges of objects in a photograph. Often, it appears where there is high contrast between light and dark objects. Some of the more expensive lenses have special coatings applied to some of their optics to reduce chromatic aberrations. This problem can generally be eliminated in software. Flare is caused when light bounces around the optics inside the lens before hitting the sensor. It usually occurs when pointing a lens at the sun or a bright light. Some lenses suffer from flare more than others. Wide-angle lenses are particularly prone to this phenomena, as the sun or a bright light is more often in the scene. One way to mitigate against flare is to use your lens hood, as it protects the front element from light entering from the side of the lens. Lens hoods also increase the contrast in our shots, and most importantly, they protect the lens from damage if dropped. In this section we talk about focus as an absolute point, rather than depth of field, which is the range of acceptable focus. This will be covered later when we talk about aperture. Most lenses sold today have autofocus, but there's still a number of manufacturers that still make manual focus lenses, particularly Samyang. These lenses still have their use today. Ultra-wide and fisheye lenses have such a deep depth of field that focus is seldom missed. When you manually focus a lens to the far extreme, you would think that the focus ring would stop at infinity. This is generally not the case, they actually focus beyond infinity. Astrophotographers often use manual lenses as they can focus on a star and then leave their focus ring for the rest of the night. Another use of manual focus will be at a racetrack where you want to photograph a car by panning. If you focus the lens on the expected position, you can pan and take the shot when the car reaches the desired position. There are still many photographers that zoom in on a static subject to check that they have the focus absolutely spot on. A good example of this would be product photography or macro photography. As I'm sure you're all aware, there are two types of autofocus. Single is best used when photographing a stationary subject, and continuous is great for moving objects. Most cameras have a variety of focus points as seen in the diagram. They generally focus on the closest point in the array you're using. Problems can occur when your subject isn't the closest point. Cameras are becoming increasingly intelligent at recognizing subjects and nailing the focus. Many cameras now sport face detection and eye detection. The latest cameras even have artificial intelligence powered autofocus that can track moving subjects at ease at 20 frames per second. As a rule, for my landscape photography I tend to be a bit old school. I use single point focus. This means I know exactly where the focus point is, rather than expecting the camera to predict where I want the focus to be. There are two types of autofocus detection. On most digital SLRs, the focus is using contrast detection. This is where the camera is looking for edges of light and dark and getting them crisp. Mirrorless cameras employ the more modern form of focus detection called phase detection. Phase detection separates light entering the camera into two separate beams. When the two parts converge, the image is in focus. This is not too dissimilar to the old rangefinder cameras that lined up lines in the viewfinder.